So on Wednesday, we did average case. We counted the number of swaps in the average case. Okay. So basically, given n, we count the number of swaps or comparisons. Okay, let's say comparisons here. We want this. Okay, count the number of comparisons and over. Okay, sorry. Count the number of comparisons over for a given permutation. Okay, and there are n factorial possible permutations. And take the average. Of this count. Take the average of this count, and that is the average case time complexity, or average case number of comparisons. You should not say time complexity, because if you say complexity, then you'll also have to include the time taken to do the comparison, how big the numbers are. You'll have to include all that. Okay. So that also can be done, but today we are doing number of comparisons. Okay. So do you agree that number of comparisons is greater than equal to number of swaps for any permutation? Okay, only after you compare, then you decide whether to swap or not. Okay. Now, so we will count the number of swaps, and if that is greater than equal to some constant times n squared. So we are currently doing bubble sort. We want to show that the average case, in the average case, bubble sort takes order n squared comparisons. So if we show that the number of swaps is greater than equal to some constant times n squared, then we would have also shown that comparisons, number of comparisons is greater than equal to some constant times n squared. And there is also that worst case time complexity of bubble sort. How much is that? Order n squared. So worst case time complexity is less than equal to n squared, some constant times n squared. The number of comparisons is, in the average case, is greater than equal to some constant times n squared. So that would mean that the number of comparisons in average case, okay, this is also a worst case, not time complexity, but number of comparisons. Okay. So it means that in average case also, it is order n squared is order n squared. Okay. Okay. So we are going to show that. Okay. So how do we show this? Now, I'll first do an example. Okay. Or let me first define the number of inversions. What is an inversion in a permutation? This is the definition. Given a permutation, sigma in Sn. I hope you remember that this is a set of all permutations from over the set 1 to n. given a permutation and inversion is a pair. So sigma, so how should you write it? Sigma of 1 is equal to whatever. Okay, 1 goes to 2, let's say 2 goes to 3, etc. So sigma of 1 is whatever, sigma of 2 is whatever. So you should write like that, okay? Or you could say, I hope you remember this. 1 goes to, let's say 2, 2 goes to 3. So this is a cycle kind of permutation. This is an example. N minus 1 goes to n and n goes to 1. That is an example. Okay. An inversion is a pair ij such that I less than j, but sigma I greater than sigma j. Yeah. So how many inversions do we have here? One and n is an example. 1 less than n, but sigma 1 greater than sigma n. What about n minus 1 and n? The n minus 1 is less than n, but n is greater than 1. Okay. What about 1 and n? 1 and n, okay, we have done. 2 and n? Yes. See, 2 is less than n, but 3 is greater than 1. Okay, so you will get all these 1 and 2 and 3 and 4 and n minus 1 n. So the number of inversions is n minus 1. Okay, so an inversion, let's underline this, is a pair ij such that I less than j, but sigma I greater than sigma j. Okay. Let I'm using this symbol I sigma in the set of inversions in sigma, in the permutation sigma. Therefore, I sigma is equal to this set, right? I comma j such that 1 less than equal to I less than j, strictly less than j less than equal to n, and sigma I greater than sigma j. So this is a set of all inversions. So what are we doing when we do the bubble sort algorithm? Now we are ready to take this example 72964. Okay, let's do it here. How many inversions are there? We should look at the pair of numbers which are smaller. I mean, 7 and 2 is an inversion. Why is that? Okay, this is about the set 2, 4, 6, 7, 9. If I write 2, 4, 6, 7 point like this, now it makes sense, right? Sigma I greater than sigma j. I less than j, but sigma I greater than sigma j. 7, 2. Then 7, 9 is not an inversion. 7, 6 is an inversion. 7, 4 is an inversion. 2, 9 is not. 2, 6 is not. 2, 4 is not. 9, 6. Yes, 9, 6 is an inversion. 6, 9, 4. 9, 4 is an inversion. And 6, 4 is an inversion. So 6 inversions. Now let us do bubble sort. Okay, I'm just going to write the swaps. Okay, so you look at this. Okay? Then 7 and 2 you compare, you exchange 2 and 7. 2 and 9 you keep them as it is. 9 and 6 you change 6 and 9. And then 9 and 4 you swap it and make it 4 and 9. So now it is 2, 7, 6, 4, 9. So there are 1 swap, 2 swap, 3 swaps. Correctly. Okay, so the claim is that whenever you are swapping, you are setting the one inversion straight, right? Here you are setting this inversion 7 to straight. Here you are setting this 6 9 9 6 straight. Here you are changing 4 and 9 9 and 4. Okay, once you set it straight, then you won't exchange it back. Okay, so the number of swaps is equal to basically the number of inversions. So we will see that. 4. Okay, 2 is less than 7. 7 is greater than 6. So do this. Now you are exchanging this. Now 7 and 4. 7 is greater. Okay, so you're setting this straight. Then 7 and 9, there is nothing. Then now tally looks like 2, 6, 4, 7, 9. And next time we are going to exchange 4 and 6. So means the number of swaps will be equal to the number of inversions. Okay, this also gives you a shortcut to count the number of swaps. You just have to count the number of inversions in the given array. So you don't have to actually run through that entire algorithm. Like in your entrance exams, you can just count the number of swaps. Oh, sorry, the number of inversions. Okay, so that is it. So now you have to count the number of inversions, okay, to count the number of swaps. And the number of swaps will give us a lower bound on the number of comparisons. So that is the idea. So how do we count the number of inversions? Okay, so now you have to look at, okay, the number of inversions depends on the permutation, and you have n factorial permutations. So you have to basically count the average of the number of inversions. Okay, so now we are going to go to your probability course. Okay, so I don't know whether you have used this the same notation for random experiments. So here we are. The problem is that this, okay? You have to count the expected number of inversions. What is your sample space? It is a set of all permutations over the set 1 to n is equal to Sn. Hmm? Size of Sn is equal to n factorial. And now you want to find the expected and each permutation occurs with equal probability, and you have to find the expected value, okay, of the number of inversions. So that will be our answer. Okay. Now, how do you do this? You break it into as a sum of random variables. Each xij for I less than j. Okay, 1 less than equal to I, strictly less than j, less than equal to n. This is equal to 1 if I and j are inverted. That is, and under that permutation, sigma I is greater than sigma j, and it is 0 otherwise. And x is equal to this. Okay, summation xij, and the summation is over all I strictly less than j. Okay, now by linearity of expectation, you get this. Expected value of x is equal to summation of expected value of xij. Now, what is xij? Expected value of xij. The sample spaces of this set of all permutations. My claim is that it is equal to half. With probability half, they are in the correct sequence. I comes before j, and with probability half, it is inverted. Why is that? So given any two values, let's say 5 and 6, then if we fill up this the rest of the permutations, now only these two now you have to only fill up these two integers. So either you can put 5 here and 6 here, or you can put 6 here and 5 here. Okay, so the expected value of xij is half. And how many such pairs are there? Ij and choose 2. Okay, so you get this. So we have to show that this is greater than some constant times n squared is greater than equal to 1 by 4 times n squared. Okay. Okay, so we are done. We have shown that the number of inversions in expectation or on average is greater than some constant times n squared. Number of inversions we have shown is equal to number of swaps, and number of swaps is upper bounded, or the number of comparisons is lower bounded by the number of swaps. So the number of comparisons is also greater than some constant times n squared. Okay. Yeah. So we have shown this for bubble sort. Now, what about insertion sort? Insertion sort, the argument is the same. Number of comparisons is greater than number of swaps, and we will add what is the number of swaps? Again, it is equal to the number of inversions. So I just have to show that now. Okay. And again, the number of inversions, if we go over all permutations, we have seen that the number of inversions is greater than n squared by 4. Now, what remains is to show this, that the number of inversions is equal to number of swaps for insertion sort. First, let us do it with our the same example, 72964. Okay. So let me erase the tick marks and let me do it in some other color for insertion sort. 72964 insertion sort. So 2 and so this is the initial subarray, it's sorted. Then 7 and 2, we go to 2 and 7. Okay, so this part of the array is sorted. Then we go to 9. Okay, 9 and 7. Okay, they are in the correct order. So we keep it. Okay. And then we look at 6. We want to put 6 in the correct place here. So 6 and 9 we swap. Okay, so that's what I mean, instead of just shifting, we're going to do swaps. It won't change the time complexity. Just think about it. I mean, for shifting, you will need some constant time, and for swapping, you will need some other constant time. Okay, so that's it. Again, 6 and 7, we will swap 2, 6, 7, 9. So we are keeping it like this. Okay, then comes 4. 4 and 9 we swap. See, and then 4 and 7 we swap. Then 6 and 4 we swap. So this is 1, 2, 3, 4, 5, 6. Because what are we doing? We are swapping two numbers, we are putting them right, and once we put them right, then we won't go back. Like afterwards, again, once you do this 2 and 7, you'll never come under the situation where 2 and 7, we again get back to 7 coming before 2. That is one thing. And another is, it does not affect the other swaps, other inversions in the array. For example, this, look at, let's say 6 and 9. So 6, we only exchange these two, 6 and 9. So it does not affect that 6 comes before 4. So that inversion is still there. And it does not affect that 6 comes after 7. Okay. So only its relation with 9 has changed. Only one inversion has happened. Only one inversion we have set it right. Okay. Similarly, 9 also, its relation with these or this does not change. Okay. So the number of swaps is equal to number of inversion. And then, yeah, the argument will be the same. So you write this argument on your own. Okay, I think this was a better analysis than what we did in the class. You can ignore that part and you can keep this. Okay, thank you.